Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker is Dr. Yeonjang Shin. He will be giving a talk on tLaSDI, Thermodynamics-informed latent space dynamics identification. Yeonjang Shin is an assistant professor of mathematics at North Carolina State University. He completed his PhD in mathematics from the Ohio State University. Before joining North Carolina State, he was an assistant professor at Korea Advanced Institute of Science and Technology. And before that, he was an assistant professor in the Division of Applied Mathematics at Brown University. He is a recipient of the Sangson Young Mathematics Award from the Korean Mathematical Society and a founding member of the Center for Mathematical Machine Learning and its application, CM2LA, which was established as a science research center supported by the Korean Ministry of Science and ICT in 2023. With that short introduction, the floor is yours and you can start your presentation.
First of all, thank you so much for kind introduction and quite lengthy and mouthful. And always glad to be speaking at the Francis seminar. So today we're going to talk about one of my recent work on thermodynamics, which is based on joint work with Richard Park, who was my postdoc when I was at KAIST. Now he's starting his tenure track at Korea University, Sejong campus, and two other folks, Tony and Youngsu from Lawrence Livermore. So the motivation might be illuminating, but let me just go over. So we trying to apply this thermodynamic framework in high-dimensional cases. And one of the challenges, even if you know what is the governing dynamics, is quite computational challenging. So even if we know F, then when we're trying to solve this high-dimensional ODE, we may want to apply numerical integration. Due to stability issue, we may want to apply backward Euler. Then the problem is you have to solve this nonlinear equation. Typically, when F is nonlinear, then the thing is that Newton's method requires Jacobian, so that's why it is computationally very challenging. Then there must be an alternative that solves this high-dimensional ODE system. And one alternative and popular framework might be, while there are many variations of the name, might be the reduced order model. So a reduced order model may be thought of as an efficient way of approximating or simulating this high-dimensional dynamics. So idea is, all right, since the dimensionality is an issue, so let's reduce the dimensionality. So now dimensionality comes in, so that ROM consists of these three components. One is encoder, decoder, and dynamics. So encoder is essentially reduced the high dimensional state into the smaller dimensional state, which is called the latent space, which is a small d. And now with this z variable now being reduced so that we can construct the dynamics in this small d dimensional space. Now this dynamics is in small dimension so that we can solve it efficiently. And now after this being evolved, then we can just decoding back to map to the full dimensional, high dimensional space. So computational bottleneck has been resolved if we have this mechanism by solving dynamics in low dimensional space. So that's the general reduced order modeling framework. Then the question is, then how do you build encoder, decoder, and the dynamics, the latent dynamics? So yeah, so reduced dimension give you computational advantage. So popular approach may be categorized into the two part. One is the encoder, decoder, so which how do you reduce the high dimensional object into smaller one? So this is maybe thought of as a dimension reduction techniques. So traditional, maybe standard way might be the POD, singular value decomposition wide, and truncation approach, and maybe more popular way in recent days might be autoencoder. And building latent dynamics is also quite a mouthful. Maybe one standard approach might be least square-based projection method. And when it comes to the nonlinear problem, then hyper-reduction technique has to be introduced. And this is not the main part of the talk, but you may see this S optimality is the one I developed. And someone might guess what S represent looking at my last name. And more recently, the data-driven approach used machine learning and SIMD, etc. So a little bit of this SMality is if you search the optimal experimental design in Wikipedia, then this SO optimality is the one that I developed with Dongbin a long time ago. So initially, it was proposed as a UQ method, but now reframed it as the ROM method as a hyper-reduction technique. So that if you're interested in, maybe you can also try it out with this libROM library, open source. But today's talk, I will going to talk about this autoencoder and machine learning approach. So more specifically, I will going to talk about what kind of advantage we may get if we model this latent dynamics using thermodynamic structure. Then naturally, two questions arise. One is that how to define a loss function, or more mathematically rigorous way of defining a loss, because now we have encoder term and decoder term, so that there must be some rigorous way of defining a loss. And second one is this thermodynamics, and how do you embed thermodynamics, especially for parametric case. So first, let me talk about then how do we define the loss function. So suppose this is our full state dynamics, x dot equals to capital F of x. So xt is our true solution, which is our goal to approximate. But since x state defined in high dimensional space, so that let's apply encoder decoder. So when you apply the encoder, then you have a z in latent dimension, latent space. So that let's say z dot is the latent dynamics. So the blue is the latent dynamics, and initial condition is coming from the full state through encoder. So initial condition is determined by the full state and encoder. But what we are actually interested in is how the approximated dynamics is close to the full dynamics. So in other words, let's say xt, the zt, is the latent dynamics evolved with the time. And then after fully resolved, they're decoding it, get the x hat t, which is the red arrow. Then the question is then how x hat t is different from x. So once we quantify the differences between the two, then the upper bound might be a good candidate to be used for the loss function. So essentially what we have derived an abstract error estimate in which it reveals the four terms, and we discretized it and use it for tLaSDI. Somewhat surprisingly, maybe not, but these two are actually the standard loss terms that people frequently adopted in the literature. Essentially, the reconstruction part is coming from autoencoder, and integration is the standard loss term that used in dynamical data-driven discovery of the dynamical system. And some also the modeling error also somebody was proposed before. But what's new is this Jacobian term. So essentially, the Jacobian term ensures something intrinsic property of the dynamics, so that these are specific terms. At the end, we discretizing it and use it as a loss function. So I was going to mention briefly later that one of the core part is that we're going to train autoencoder and dynamics simultaneously. And I will tell you why that is the case in the numerical section. So that is the one thing that how we define the loss function. And the second part is that when we define the latent dynamics, one of the big question from the beginning of this work was that why thermodynamics has to be embedded in designing latent dynamics, like because there are many other choices out there. you can just simply use a feed forward neural network or transformers or maybe DeepNet, FNO. There are many choices out there, but why particular choice of this thermodynamics you may want to consider. So one thing is that this is a famous book, The States of Matter, and the very first page, it says, basically thermodynamics is quite challenging theoretically. So this stands it as a challenging topic still, and hasn't made many progress theoretically. So found that this might be a perfect framer or formalism that we can combine with the data-driven era. And furthermore, there is so-called generic formalism that states that the dynamics may be written as this certain structured form utilizing the four functions L, E, M, S, and each has their own meanings, physical meaning, energy, entropy, Poisson friction matrices, but there are four constraints that ensures that this dynamics satisfies the first and the second order, second laws of thermodynamics. So inspired by this formalism, George and I and former grad student Jen, we actually proposed a generic formalism informed neural network published in this Philosophical Transactions, Royal Society A. And there, what we designed is that we designed each and every component of the generic formalism and ensures that these four conditions to be satisfied for any parameters before any training. So it's sort of like structure preserved model, and also show that the proposed architecture satisfies the universal approximation. And at the end, so this is the right-hand side of the model using neural network that carries out this generic formalism. So L is a neural network under certain type, E is same, M, S at the same time. So in conclusion, tLaSDI came out maybe straightforward approach. All right, let's apply autoencoder to train encoder-decoder part, and also use the GFIN in modeling latent dynamics. So, and then trained over the loss function that we proposed, and let's see how the results look like. So in a nutshell, this page shows what is the tLaSDI in a higher level. So before I move on to the numerical example, are there any questions from the audience?
Yeonjang, I have a question. Why the latent dynamics have to satisfy the generic framework? How do we know that?
That's a very good question, George. So, okay, simple answer is we don't know. So one part of the goal for this project was, let's see what kind of advantage we can get by using or enforcing thermodynamic structure into latent. And I will show you some partial observation we gained from numerically.
Because one of the problems with it is that when we go to latent dynamic space, we don't know actually what are the governing equations, right?
Exactly.
Uh, so it is a $1 million question if I can understand that the results are better and so on, but I'm asking from the fundamental point of view. I think that's definitely an open question, right?
Right. So still I'm looking for an answer so that maybe some of the numerics giving some insight on that, because in the later I will going to show the 1D Burgers equation example, and that part actually Young's and I had a discussion on. I mean, why do you want to solve the Burgers equation using thermodynamics? And but we found something interesting
Well,
using that.
the implicit one is important for the implicit one because, for example, you need the entropy inequality for implicit burgers.
Right.
For the viscous, I don't see the point, but for the implicit, there is.
Yeah. I will. Maybe we can bring that discussion later when I show that example
Sure,
a
sure.
little bit more. Yeah. So we first try this Aldridge-B fluid example so that we focus on extrapolation task. One of the reason is because other method actually works then for interpolation regime. So that's the honest answer, but we wanted to see what kind of benefit we can expect by enforcing certain structure. So this example is coming from the thermodynamics, so that we should expect something better in extrapolation. And not too surprisingly, we do better, so that we compare with the tLaSDI and also some similar approach that being proposed. This is the structure preserving neural network. So this is one of the first architecture that tried to embed generic formalism into the neural network, but through some penalty terms. And then their approach used slightly differently. So first they train autoencoder first, and then as a second step, trying to learn the latent. So this is the red. And vanilla FNN is we just try to see what kind of benefit we can get if you replace the GFIN to just a fully connected neural network. And these are the result. And you can see that, so there's a certain black dashed line here, and that indicates that this amount of time being spent for training autoencoder. And for the rest is trained with standard loss for SPNN, which is another architecture. So this might be not that bad. We are showing the relative L2 error on extrapolation regime. And this is how the H trajectory look like. And you may see that peak and this V are not too bad because they are linear behavior, but found that this tau is quite difficult to capture because there's some wiggly behavior along the line, but that is still quite hard to capture. But overall, perform better than what you can get from other models. And similar, the gas container example. So we also do the similar thing, tested on extrapolation to see how well the model performs. And definitely we see consistently better result for this tLaSDI. We also run the multiple experiment and then showing the mean and standard deviation of the relative L2 errors. And a similar story hold. Yeah, and this is the example that parametric 1D inviscid Burger's equation. So that compared to what has been out there, GLASDI, the tLaSDI giving you the better performance. And the black squares indicates that because there's some adaptive sampling strategy for how you choose which parameter to train, because there are many parameters. So some, that adaptive sampling strategy being applied for both. And as a result, we get a smaller loss, smaller error. And that is the part of what you asked about. So we paused after we see this result, we paused a little bit more, paused and think about what kind of other benefit we can extract. So first thing I was trying to see was the energy, but there are not many things we can extract from the energy because energy is constant because the energy being preserved. And so that's why we both take a look this entropy function. So we first draw the entropy, but it's not that surprising because entropy is always increasing, so that the left figure doesn't tell much. But in the literature, it turns out that this entropy dt, so derivative of the entropy with respect to the time, is called entropy production rate. And seems that this quantity has some importance in certain field of physics, so that we decided to draw how this entropy production rate behave. And you can see that entropy production rate, this has to be always positive because entropy is increasing. More strictly, no negative. And we found that when time equals to 2, the entropy production rate is somewhat suspiciously high. So we go back to see how the full state look like. And in fact, this is the time where the full state dynamics almost form a shock. So that is the when time t equals to 2 case. So with that example, we got surprised by this result, so that we did one more test. So without touching anything, we changed the dynamics to heat equation. So when you change the dynamics to the heat equation, everything diffuses out so that as the time process, nothing interesting happens in the full state. So as a matter of fact, if we draw the entropy production rate, the most highest rate actually occurs at time t equal to 0. And as time goes by, actually goes almost comes down to 0, which is the match with how the heat equation might behave. So that is the part, George, I was talking about. This might have some connection to the why thermodynamics in latent. So some working hypothesis at the moment is that maybe when you incorporate the thermodynamics into the latent, then maybe this entropy, the latent entropy function, which somehow learned function, may giving you an indication of some stiff behavior of the full state motion. And then this is somewhat most recent extension to say, so all these example autoencoder part, actually we use so-called hyper parameters, so hypernet. So meaning that if we want to learn parametric cases, parametric PDEs, there must be some part that incorporate the parametric motion. So in earlier, we incorporate the parametric dependency through autoencoder while maintaining the same GFIN, but turns out that that is quite computationally expensive. So that recently we proposed some simple extension, which is the parametric GFIN, because hyperautoencoder is expensive. So that idea is the following. So if the thermodynamics depending on the parameter mu, but parameter is somewhat fixed part variable, so that mu dot equals to 0. So motivated by this equation, we just take GFIN, each component of the GFIN, mu as an input as well, along with the z, and then just rewrite out the generic formalism. So now new generic formalism take the parametric input as well, but when you calculate the gradient, we only take the gradient with respect to z, while just mu seems like the dummy variable at the moment. But when the training kicks in, then we can manipulate each component according to the parametric cases so that adjust the dynamics accordingly. And we apply this parametric GFIN in the tLaSDI framework and see how it looked like this 1V plus a Poisson equation. So here, what we made it parametric is this F initial condition, so that mu include the temperature T and the wave number K. So this is the two-stream instability, so that time 0, just a two-stream. As the step goes by, then instability occurs. So this is how the solution look like. So when we compare with this hyperautoencoder case versus the parametric GFIN, and we see that we get slightly better average error, but 90% reduced the training cost. So HyperNet is quite expensive in that case. And also, we also looked at what this entropy does with respect to the parameter. So here, left, I'm showing you the entropy figure with respect to the time steps. And here I fixed the temperature 0.9 and varying the K. And that is this case, so fixed temperature and increasing wave number K. Then we see that we have higher initial entropy, but lower final entropy at the end. So that is when you see this, the purple line, so that is the initial shape. So K is the largest, initially, but at the end, actually K is the lowest level in terms of the entropy. And similar behavior was observed when we fixed the K and varying the time, the temperature, then same conclusion hold. And then we reach out to the physicists to see whether this interpretation makes sense, and we got confirmed that this is quite consistent with the known plasma physics behavior, saying that increasing T and K suppress the gross two-stream instability. So, and also similar thing, we also plotted the SDT, the entropy production rate. So this figure corresponding to this blue curve, so that there's a quite oscillatory behavior, but when we match with what's going on in this peak, this peak, this peak, and quite consistent with how this stream undergoes some changes, but lack of some physical background. So we couldn't really make a big any conclusive statement, but this is what we have observed. Then that's it. Summary is the tLaSDI autoencoder plus GFINs. So loss function comes from abstract error estimate, and we found some intriguing observation saying entropy production rate has some correlation with the full state behavior. So these are the references, and I'm happy to take any questions.
Thank you so much for your presentation. Now we open the floor for questions. Do we have any questions from the audience for the speaker?
Oh, hi.
Alan, yeah.
I had a question. I'm a PhD student with George.
Hi.
Yes, so similar to the question George asked, I was wondering whether like enforcing the thermodynamics constraint in the latent space is equivalent to enforcing it in the original physical space. So have you like done any comparison with models that enforce the constraint in the original space, like GFINs directly or something?
Okay, simple answer to that is no, we haven't done it because GFIN is quite expensive. So that the full state applying GFIN is sort of like out of memory at the moment.
Okay. All right.
So that hasn't done. But a couple of colleagues asked similar question. If the full state follows the thermodynamics, then can you ensure that full state is guaranteed to satisfy the same property? And unfortunately, delving into the analysis, unfortunately, the answer is no. But to some extent, it might be possible. But at the moment, I should stick by no.
Okay.
But can be done approximately, I would say.
All right. Okay. And like one more quick question. So in the latent model that you have, how expensive is the Jacobian term? Like, how does that scale with the number of particles or the dimension of the problem?
So that is done in latent dimension, so that the computation cost is not too bad because you can either use the JAX, the VBP.
Okay.
So the Jacobian computation is not very computationally challenging, that part, because now everything is taken with respect to the latent dimension, unless latent
Oh, I
dimension
see.
is still high. Yeah.
Okay. Okay. Yeah. Sounds good. Thank you.
Yeah.
Okay. Do we have any other questions for the speaker?
Yeonjang,
Yes.
one guy wrote some comments about solving the Vlasov equation, 1D Vlasov equation with pins, and he said he failed. The pins failed to do that. Have you guys tried to do that without any
Data.
thermodynamics? Yeah, just to try to solve the 1D Vlasov equation, the one that you had.
Just a pure pin, right?
Yeah.
No, we haven't done it, but I see some challenges. But yeah, the simple answer is no, we haven't. It's all the part I present so far is data driven.
Right.
But are there any literature we're able to solve this the plasma physics using pin?
Well, one guy was about mouthing pins. So he said he was from Princeton, and in his thesis he tried to use pins to solve this equation, and he couldn't. I, uh, I don't see. I mean, I don't see the difficulty actually. Um, but if it's one dimension, the
I think
last
should
term,
be, yeah,
the
yeah,
last
I
term
think
would
so.
be v
Yeah,
would be scalar, right? So,
right.
um,
Oh, yeah, I think with the pin 2.0 should be able to do that because it's a 1D. So how bad it can be. So I don't really see at the moment by looking at the
yeah,
equation
with the second
any
order optimizer, and
right. And
RBA,
also,
yeah.
yeah, residual-based attention is really powerful. So
Yeah, Raj wants to have somebody to solve it, so we'll see. I thought you guys have tried, but
not at the moment.
Okay, do we have any other questions for the speaker?
Maybe
I don't.
I want to ask one question to George. Do you think this happened to be by accident or there might be some reason behind?
not accident.
I see.
There is a correlation. There's a correlation. I mean, the results are factual. My question was more like, I mean, we asked. I think with Yanis one time, he asked also Yanis Kivrakidis. He asked, in which cases the generic framework
Mhm.
is applied. Is it for all dissipative systems on Earth, or is it so what subclass? And I think somebody wrote a paper about it. So I remember somebody
Oh,
sent me a paper when the generic framework is applied, and the, of course, in the latent space, you don't know how these models end up looking, and therefore you don't necessarily even monotonicity, right? Even if you have monotonicity in the state variables in the original space, in the latent space, you don't know if that state variable is monotonous.
right.
It is an open issue, I think.
I see.
But but the results look appropriate. Of course, you have a shock there, and therefore you expect that and the entropy, you sort of impose an entropy condition that is appropriate. That has been observed.
I see. I see. Yeah, thanks. Yeah, thanks.
Okay, I don't think. Is there any other questions? I don't think so. Any comments?
Maybe I have a question.
Okay, go ahead.
Can you, there was a part when you were showing, you said that you were using adaptive sampling
Right.
thing, but you said that you do it in the parameters, so I didn't follow that part that much. So you explain that again?
Yeah, sure. Okay. For example,
I think it
all
was
right.
here.
Yeah. So for example, there are a couple of choices so that you wanna trying to learn a solution to this PD with the varying, let's say this parameter mu. Then to do that, you gotta to sample for the data purpose, data generation purpose. You gotta generate the data at somewhere in the domain of your interest. So one simple way, maybe you can do just a random sampling or just a grid, generate the grid and train over it. But that turns out to not as efficient as what it looked like, so that people have proposed various adaptive sampling method, maybe starting from point, uh, maybe 4 point through the end, and then apply some training and under certain criteria met and see which parameter yields the higher error and then sample there and repeating the similar process.
So it's like for the data generation mainly.
Yeah, so mainly reducing the number of the data generation.
Oh, okay. But then it would mean that after every round of this sampling, you would need to train and retrain your model, right? Like refining and refining, or
Yeah, in a similar mechanism. Yeah.
oh, okay. Sounds interesting. Thank you.
Yeah.
Do we have any other questions? No. Thank you so much for your great talk and your time to
right.
join our seminar. And thank you everybody for being here today. It's time to close the session. Have a great weekend ahead. Bye.
Thank you.